Profesor Nicolás.
No se oye.
Ok, no estamos escuchando, Nicolás.
Hola. ¿Me
Ahora
puedes
sí, por
escuchar?
ahí te escucho. Sí,
¿Me
ahora
puedes
sí.
escuchar?
Ahora sí.
¿Funciona,
Sí.
¿funciona ahora? Sí. Bueno, no sé
Sí,
qué es lo
sí.
que pasó.
Ok, muy bien. Puedes ir compartiendo, por favor, Nicolás, y me das unos segundos para presentarte, por favor.
¿Aquí puedes ver mi pantalla?
Sí, estamos viendo perfectamente las dos ventanas. Bien, bueno, todavía faltan 4 minutos para iniciar. Voy a hacer una pequeña presentación, ¿no? Con calma y aprovechando esos minutos, ¿no? Estimados asistentes, es un honor presentarles al profesor Nicolas Dutertre. Profesor Nicolás es un investigador, trabaja en Francia. Con él hemos tenido la oportunidad de conocernos. Bueno, él mayormente trabaja con el grupo de singularidades de acá de São Paulo. Y hemos tenido la oportunidad pues, de conocernos acá en particular en este año, y fue donde amablemente aceptó, ¿no?, en darnos una charla. El profesor Nicolás me comentó pues que no tenía comunicación, contacto con alguien de Perú, ¿no? Y en particular pues fue una alegría, ¿no?, de poder tener a Nicolás de esta manera, ¿no? Esperamos que tal vez en alguna oportunidad, ¿no?, ya sea en la forma natural, presencial, ¿no?, de tenerlo por Perú. Profesor Nicolás. Profesor Nicolás trabaja también en esta línea de singularidades, ¿ok? Entonces, también le estoy hablando en español porque el profesor Nicolás entiende español, ¿sí? Así que pueden, por favor, estimado público asistente, con la confianza de preguntar al profesor Nicolás, ¿no? Tengan la amabilidad, ¿no?, de la confianza de hacerle cualquier duda, inquietud que tenga, ¿sí? El detalle que su charla, ¿no?, también sea de forma fructífera y del máximo provecho para cada uno de nosotros. ¿Ok? ¿Ya? También cualquier dificultad que tal vez se presente, ¿no?, pueden hacerlo notar, ya sea en el chat o avisando, ¿no? De cualquier forma, o nos pueden avisar también. Ya, los que aparecen como coordinadores ahí en el Zoom pueden escribir tal vez directamente ahí, ¿ya? Y no se olviden que la asistencia siempre vamos a compartirla casi minutos antes de la charla, ¿ya? Ya les van a dar por ahí, creo que les pasaron la información del mínimo de asistencias que deben tener para el respectivo certificado sea general. ¿Ok? Muy bien, Nicolás, tienes 50 minutos. Ya, muchas gracias por esta oportunidad que nos estás brindando en compartir parte de tu trabajo. Adelante, por favor.
Bueno, muchas gracias, César, por la presentación. Es un placer hablar aquí en un congreso en Perú. Bueno, voy a hacer la presentación en inglés, es más cómodo para mí. So, I'm going to talk about semi-algebraic functions with non-compact critical set. So this is a joint work with Juan Antonio Moya Pérez de Valencia. So I don't know what are your knowledge about singularity theory and semi-algebraic set. So I will record some basic facts about first about stratification. So. So I will first present witness stratification. So I consider X semi-algebraic set. So as Edson explained in his talks, it is a set defined by a Boolean combination of polynomial equalities and inequalities. So it's a very common common kind of sets. So I equipped it with a finite witness stratification, or it's also called B stratification. So what is a witness stratification? So first, it is a partition into a finite partition into smooth pieces, VA, where each VA is a smooth semi-algebraic manifold. And the frontier condition is satisfied. So what does it mean? So if a strata VA intersects the closure of another strata VB, then this means that VA is included in the frontier of VB. So I will give here, I will make a picture to illustrate this frontier condition. So imagine here I have a stratum VB, another stratum here, and another stratum here. And I assume that VA is the interior of the triangle. Then here the frontier condition is not satisfied because maybe I should have, right? Yes. This is VA and this is VB. So here VA is not included in the frontier of VB. Here. And to get the frontier condition, I should add here zero-dimensional strata and split the strata VA into two pieces. So this is the frontier condition. And there is another condition which is more geometric, which is called B condition, condition B. So if I take VA stratum in the frontier of another stratum VB, then the following condition is satisfied. So I take a sequence xi of points in VB that tends to a point y in VA. I take another sequence yi of point in VA that tends to another point y in VA. Then the following should be satisfied. I assume that the line that passes through xi and yi tends to a line L, and the tangent plane to xi at the strata VB, the tangent plane to the strata VB at the point xi tends to a set plane T. Then the following inclusion should be satisfied. L should be included in T. So I will make a picture where this condition is not satisfied. So imagine you have this set. Oh, sorry. This set. Okay. And here there is a line. So if I take a sequence of points, so here, this is VA is a line here, and VB is this part here. I have the sequence, the point here, xi. Here it's yi, and the line is a vertical line. And I take a sequence that converges this way. So at the end, my line L is vertical, but here the tangent plane to the strata VB, the tangent planes, they will tend to an horizontal plane T. So here, the line L is not included in the space T, so the Whitney condition B is not satisfied. So if you want to have a Whitney stratification here, you should add another strata here, another stratum here, by putting a point. Okay. So this is a Whitney stratification of a semi-algebraic set. So this is a very important notion in singularity theory and semi-algebraic geometry. So now with this notion of witness stratification, I can give I can state an index theorem for a semi-algebraic set that may be singular. So I consider X a closed semi-algebraic set in Rn, and I equip it with a finite witness stratification. So X is the union of strata Si, SA, and I consider F from Rn to R to be a C2 semi-algebraic function. For example, it can be a polynomial function. And I define in this situation, X is not a smooth variety. So I should define the notion of a critical point in this setting. So we say that the point P in X is a critical point of the restriction of F to X if it is a critical point of F restricted to the stratum that contains P. Okay, you have a decomposition. You decompose a set, a closed semi-algebraic set, into a finite number of smooth pieces, and the critical point is a critical point of F restricted to one of these smooth pieces. Okay. So now I can define the notion of index of F at a critical point. So I assume that P is an isolated critical point of F restricted to X. Then the index of F at X restricted to P is this quantity 1 minus the Euler characteristic of X intersected with a small level, with a level Fp, F equal Fp minus delta intersected with a small ball, and the condition are that delta is very small respected to the radius of the speed of the ball, which is very small respected to 1. So let me give an example of an index. What is this index? This index. So imagine that this is my level F equal Fp. So here it's just this curve. P is this singular point. I draw a regular level close to my level. So this is here. This set F equal Fp minus delta, and I intersect with a ball centered at P. So here you see that the index is 1 minus 2. So the index is minus 1. Okay, so this is a general way to define, to associate an index to a critical point in this singular setting. And remark, if X is smooth and P is a non-degenerate critical point with Morse index lambda P, then this index I define with the mean of the Euler characteristic is just -1 to lambda P. So we recover the notion of index of a usual non-degenerate critical point. So how can we relate this index to the topology of this set X? This is the following theorem. So I assume that X is compact and that the function F restricted to X has a finite number of critical points, P1, Pk. Then the relation between the topology of X and the critical point Pi is given by the following formula. The Euler characteristic is just the sum of the indices of F on X at each point Pi. So I will not give the proof of this result. I will just make a picture in an example to illustrate the theorem. So consider my set X is a full parallelogram. So this is a parallelogram within its interior. That. So it has one stratum of dimension 2, the interior, 4 strata of dimension 1, the edges, and 4 strata of dimension 0, the vertex, the vertices of the parallelogram. Okay. So here I have strata of dimension 0. And I will take for F the projection on this oriented line, which is R. So this is F. So where are the critical points? There are no critical points in the interior, no critical point on the edges, but the 4 vertices are critical points. Because the 0-dimensional stratum is always a critical point. So let's compute the indices. So here, what do? I write a small regular level here, left level, let's say, close to the point. Here, this is the value FP. Here, this is the level FP minus delta, and I intersect with a ball, with X and a ball. So we see here that the fiber does not intersect X. So the other characteristic of the fiber with intersected with X is 0. So the index is 1. Here we have index plus 1. And here I compute the same way the index. Here I draw the fiber, the nearby fiber. I intersect with the ball here. And what we should compute is this set. We should compute the other characteristic of this set. So it is 1. So 1 minus 1 is 0. So the index is 0. Here, index is 0. Okay, I do the same thing with this edge, with this vertex here. Okay, the fiber is here. I intersect with the ball. So here, the other characteristic of this part is plus 1. So the index is 0. And here, you see the same phenomena occur. Here, this is a nearby fiber, the ball. And the part we are interested in is this one. So it has a characteristic 1. So 1 minus 1 is 0. So yes, we find that the other characteristic is 1, which is coherent because the parallelogram has a other characteristic 1. So now let me give another example. Here I will remove the interior. I will just consider the parallelogram. So we have 4 vertices and 4 edges. I consider the same function, just the projection on this oriented line. And I compute the indices. So the fiber are here. The fiber is the same, this one. The ball is the same. And the index is always a plus 1. Okay, plus 1. Here, fiber as that. I draw the ball. And here, the intersection is just 1 point. So the index is 0. And similarly, here we have we will have 0 for the index. So 0. And here we have this situation, this picture. And here you see we have 2 points in the fiber. So the index will be 1 minus 2 minus 1. So we find that the Euler characteristic is 0. And we recover the Euler characteristic of parallelogram. So this was just a proof. This is not a proof of the theorem because the proof is is quite sophisticated, but just an illustration on an example, on 2 examples. So my aim today is to present generalization of this result, this index theorem for the Euler characteristic of a closed semi-algebraic set. So this is what I'm going to explain in the sequel. I have to choose this window. So now I will generalize this result to closed semi-algebraic sets. So I remove the compactness hypothesis. So I consider X a closed semi-algebraic set, and F, as before, is a C2 semi-algebraic function. I equip X with a finite witness stratification. So X is a finite union of the strata SA. So this is the situation. Now I have to define a set that will describe, let's say, the topological behavior of F at infinity. So I choose star to be one of these 3 symbols, smaller than or equal, equal, greater than or equal. Okay, and I define this set. This is lambda F star. So this is a set of points where the set of points alpha in R, where the following function is not constant in a neighborhood of alpha, and the function is the function that assigns to beta the Euler characteristic of the link at infinity of X intersected with F star beta, which means F equal beta, F greater than or equal to beta, or F smaller than or equal to beta, where the link at infinity is the intersection of the semi-algebraic set with a sphere of sufficiently big radius. This was explained in before, just before in Edson talks. So let me just give an illustration. For example, imagine that I have this function. This is, for example, the level F equal alpha here in black, and in red I defined a nearby level. But imagine that it does this figure, this picture, and here alpha, this goes to infinity. So let's say this is F equal beta. So you see that there is a jump in the Euler characteristic of the link, because here for F equal alpha, the link will, imagine this is a big sphere, like that, or very big. So you see here that the link is consists of 4 points. But here on the fiber, for the fiber F equal beta, we just have 2 points. So you see that some phenomenon can appear at infinity where the topology of the link at infinity can change. So voilà. Sorry. So the first lemma is that these 3 sets are finite. So there is only a finite number of value where the topology of the fiber at infinity can change. So if, for example, I will focus on the set lambda f smaller than or equal. So it is finite. So I can write it b1 br, and I can order the value. So b1 is the smallest one. It's smaller than b2, etc., which is smaller than br. And I write the complement of is there any question? No. So the complement of lambda f, I write it as a union of interval b0, b1, b1, b2, union, etc., br plus 1. And b0 is minus infinity, and br plus 1 is just plus infinity. Now I take for each j between 0 and r, I take value bj plus that belongs to the interval bj plus 1. This is a generic number of the interval. So what is the result now? So this is the result I proved first in 2012, and then with Juan Antonio Moya Perez. We gave us a different proof in 2016. So let us assume that f has a finite number of critical points, p1, pk. Then how can we relate the topology of x to those to these critical points? So the formula is the following. So you see, as in the compact case, we have first the Euler characteristic is equal to the sum for I equals 1 to k of the indices that I define, all the indices of f at the critical point. And then there is a second part that comes from the topological changes of that appears at infinity. So the second part is the sum for j equals 0 to r of the Euler characteristic of the link at infinity of the fiber x intersected with f smaller than bj plus minus the sum for j equals 1 to r of the Euler characteristic of the link at affinity of x intersected with f smaller than bj. Okay. Here, this is the part. The last sum is the part where the topology of is the points where the topology of the fiber at infinity changes. So this is the formula that I proved first, and then with Juan Antonio we give another proof. So I will not give the proof in details, just give a very, very quick idea of the proof. So I choose R such that sufficiently big such that the Euler characteristic of X is equal to the Euler characteristic of X intersected with a big bulk. This is always possible for closed semi-algebraic set because they have a conic structure at infinity, like as Edson explained. And I apply the first index theorem here to this set X intersected with the ball. So we have that the Euler characteristic of X. So we can make a very rough picture. So X, imagine X is my page here, and my ball is here. So this is X intersected with the ball. Here I have the critical points of X restricted to X. So they lie in the ball because they appear in a infinite number. And here I have a boundary, and there are critical points that can that appear also on the boundary. Like that. And the strategy is very so what I denote IR is the contribution of the critical points that appear on F restricted to the critical point that appear on X restricted to on X intersected with a big sphere. Okay. And the last step is to evaluate this IR as R tend to infinity. And this is quite natural that this IR is related to the jump of the Euler characteristic of the link at infinity. Yeah, so this is just so this is not a proof. This is just an idea of the proof and an idea of the strategy I use to prove this result. So then we can do the same for the set lambda f equal. It's finite, so I can write it gamma 1, gamma t, with gamma t smaller than gamma 2, gamma 1 smaller than gamma 2, smaller than gamma t, etc. The complement of lambda f equal, I write it gamma 0, gamma 1 union, gamma 1, gamma 2, union, etc. Gamma t plus 1. And here, gamma 0 is minus infinity, gamma t plus 1 is plus infinity. And for each t between 0 and t, I choose a gamma j plus a generic number of gamma j plus 1. And so what happens in this situation? So the assumption is the same. I assume that f restricted to x has a finite number of critical points p1, pk. Then, okay, I have this formula, so you can read it. 2 times the Euler characteristic of x minus the Euler characteristic of the link is the sum of the indices of f, but also of the function minus f. And here we have the jump in the Euler characteristic of the link at infinity of the fiber f equal gamma j. Here. Instead of the sign smaller than or equal, we have an equality. So this theorem B1 is a consequence of theorem A1 and Mayer-Vietory sequence. So let me give a remark now. What happens if x is r to the n? Then in this case, the sum of these indices here, so this is the same picture because here my example x is r2, is the degree at affinity of the gradient of f, which means just this sign at degree infinity gradient of f is the topological degree of the mapping gradient of f divided by his norm around the big sphere here. I have a big sphere, board. Here inside I have the critical points of my function. Here it's a gradient. Maybe it's like that. This is the gradient of f, and I have this mapping gradient of f divided by its norm. And here I have the unit sphere, and this is a SR. This is the unit sphere. And here we have a mapping from a compact manifold to a compact manifold oriented. So we have a can associate a degree, mapping degree. This is a Brauer degree. And in this situation, the sum of the indices is exactly the Brauer degree of this mapping nabla f divided by its norm. So in this situation, we can rephrase our result. So here x is R1, so I consider f from Rn to R2 a C2 semi-algebraic function with a finite number of critical points. Then this is just rewriting theorem A1 using the fact that the Euler characteristic is 1, and the sum of the indices is just a topological degree of at infinity of the gradient of f. So this is theorem A1 restated in this situation. And moreover, so if n is even, so if n is even, then we have this formula. Okay. We can explain 2 is 2 times the degree plus the sum of the link. Here x is Rn, and here also x is Rn. And so this is a result when this is a theorem B1 when x is Rn and n is even. If n is odd, theorem B1 is just everything is equal. So for n equal to, this lossless equality was first proved by Sekalski in 2005. And yes, this was my inspiration for all of this work to generalize this formula proved by Sekalski. This is the inspiration for this work. So we can also prove other formula. Instead of using the Euler characteristic, the jump of the Euler characteristic in the link, we can also consider the jumps between the Euler characteristic of the fiber, the total fiber. So by R theorem, so this is a very famous theorem in semi-algebraic geometry, there exists a finite set BF included in R, such that over each connected component of R minus BF, F is a trivial semi-algebraic relation. So this means that except at a finite number of value, there is no changes in the topology of the fiber of F. So I write this bad set BF bifurcation set as a D1 DS. And also I write its complement as a D0 D1 union D1 D2 union etc. DS plus 1. And D0 is minus infinity. DS plus 1 is plus infinity. And we have a third theorem. Yes, sorry. For j between 0 and s, I choose a dj plus value in the interval dj plus 1. Good. Now theorem C1. So I assume that f restricted to x as a finite number of critical point P1, Pk. Then we have this formula. Okay. So here, first part is always the Euler characteristic of x. Here we have the sum of the indices of f and minus f at the critical point. And here we have the jumps between the Euler characteristic of the fiber. Okay. Here I replaced, instead of having the links, I have the fiber of the function. And here, this part of the sum is concerns the value where the topology of f may change. Okay. So this was all these theorems C1, A1, B1, and C1. They were proved by myself in this 2012 paper, and then reproved with Juan Antonio with different methods in 2016. So now my aim is to remove the last this hypothesis, this unique hypothesis, the F has a finite number of critical points. So we will remove this hypothesis and see what we can do. So now I will generalize those results to functions with non-compact critical set. So this is no hypothesis on F. This is just what it means. So from now on, we do not assume that F restricted to X has a finite number of critical points. So what can I define? What kind of index can I define? Can we define here? So I take C critical value of F restricted to X, and I will associate an index not to the critical point, because here critical points may not be isolated, but I will associate an index to the fiber of the critical value. So I define the global index of F at C by, so I denote it like that, index G for global of F on X restricted at the fiber F-1 of C. So this is the Euler characteristic of the fiber minus the Euler characteristic of a small fiber, smaller fiber, but nearby fiber, very close to C, intersected with a big ball of radius RC. So where RC is very big and alpha is a very small value, very close to 0. So if I make a picture, so this is something like that. So this is a very, here I have my fiber with critical points. Can be very singular, I don't know. I draw a very close regular fiber to it, like that. So maybe my picture is not good, and I intersect it with a big ball, like that. So this is, so the picture is something like that. So you can imagine here the picture is my fiber has only isolated singularity because my picture is in dimension 1. But you can imagine something very, very singular. And yes, here what does it mean? RC much greater than 1. It just means that the intersection of X of the fiber F-1 of C with B or C is a deformation rectangle of X intersected with F-1 of C. This is possible due to the conical structure at infinity. This means that the topology of the fiber is just is concentrated. The topology of my fiber is concentrated in a compact set, compact part of the fiber. It is concentrated in X, in the fiber X intersected with F-1 of C, intersected with a big ball. So now we can generalize our previous theorems. So this is a theorem that we proved with Juan Antonio in 2021. So here I call C1, Ck the set of critical value of F restricted to X. So there is no assumption actually, because a semi-algebraic function has always a finite number of critical value. So this is just a notation for the set of critical value. So this is not an assumption. This is always true. We have always a finite number of critical values. Then the formula is the following. So, like in theorem A1, the first part is the Euler characteristic. The second part is the sum of the global indices. This time I have to consider the global indices of F associated to each singular fiber. And then the part at infinity doesn't change. This is always the jump between the jumps between the Euler characteristic of the link at infinity of the set F smaller than Ej. So here there is no change comparative with theorem A1. There is no change in the part at infinity, but in the part at not at infinity, let's say, we have to change the indices by these global indices. Okay. So we remark that if F has a finite number of critical points, then we recover the previous result. I mean, theorem A1. Namely, if you have a critical value such as the fiber critical value C, such as the fiber F-1 of C, has a finite number of singularity or critical points, P1, PR, then then the sum of indices of F at the critical point Pi is just this the Euler characteristic of my fiber F-1 of C minus the Euler characteristic of this nearby fiber intersected with the ball. So this is exactly the index we have defined. So I can make a picture here. Imagine you have here a fiber with a finite number of singularity here. And the nearby fiber is here in red. Here I have my big ball. Then the sum of the indices at the critical points is just this difference of Euler characteristics. The Euler characteristic of the central fiber minus the Euler characteristic of this part. So we recover the first result I mentioned, the theorem A1. So, should speed a little. So let me give an idea of the proof. So for simplicity, I assume that there is only one critical value that has a non-compact set of critical points. So, and I assume that there are other critical points. What I mean by that, I assume that the non-compact part of the critical, the other critical points that do not appear on the fiber F equals C, then they are isolated. I just want to reduce the number of bad, let's say, critical fiber. So I assume that, and that's I did not buy P1, PL, the other critical points. They are isolated, and only the non-isolated, the critical point, they appear only on the fiber F equals C. So the strategy of the proof is similar to the other case. So I choose R big enough such that the Euler characteristic of X is the Euler characteristic of X intersected with a BR, and also the Euler characteristic of the fiber F equals C is equal to the Euler characteristic of the fiber intersected with the ball. I choose alpha, a very small value, positive value. And here I cannot give all the explanation. But instead of using this theorem, the first theorem that gave the Euler characteristic of a compact semi-algebraic set, I use relative versions of this first index theorem. So I have this result, the Euler characteristic of this part, f smaller than c minus alpha intersected with 4 is equal to the sum of these indices plus a contribution at infinity. So I will make a picture. So imagine this is my bad fiber. Here I have the other critical points. They are here. I have my big ball. And that. Here I have the negative nearby fiber. C minus alpha. And here C minus fiber F equal C plus alpha. Okay. So I apply a relative version of my first index theorem. I get this formula.
No, me está escuchando.
Here we have.
Ahí está, y de varios.
We have also someone is talking.
Yes, Nicolas, I'm sorry. Ya creo que está silenciado ya.
Oh.
Puedes continuar, por favor.
And here I will have also contribution. So the first equality is this one. So this in here. ERC minus is the contribution of the critical point that appear here on this part of the sphere. Here. Okay, so this is a relative version. Similarly, I can apply to a similar result for the positive part, or part greater f greater than c plus alpha. This is this part here. So here I consider this part. And here there is this term that appears, and we still have the indices of the critical point at the point pi plus a contribution from the infinity from those points here. Okay. This I have to finish. Now I apply the Mayer-Vietory sequence, and I obtain this. So this is a Mayer-Vietory sequence. I had the two equalities, and I apply Mayer-Vietory sequence. So this appears, this sync appears, but this sync is just this this part here between the two fibers, and it retracts to the central fiber. So this will give the Euler characteristic of the fiber. So this is what I explained here. This part, X intersected with this set and with the ball, it retracts by deformation on the fiber F minus 1 of C, which is a homotopy equivalent to the, it retracts first to F equals C intersected with the ball, and then this intersection is a homotopy equivalent to this, to X intersected with the fiber. Therefore, we obtain this equality. The Euler characteristic of X is the Euler characteristic of the fiber F equals C minus this intersection with F intersected, F equal to C minus alpha intersected with VR. The indices of F at the isolated critical point, and these parts from infinity. And then to finish the proof. So here, this is exactly my new global indices index. And this, we just have to evaluate the last part of the sum, IRC plus and plus IR C minus. Then we just have to evaluate this as R tends to infinity. So maybe I should finish. So theorem B1 and C1 have also generalization. I just show them. And the generalization is the same. Each time we replace, in each of the equality, we replace the local indices by the global indices. And we get the same forms. And similarly for theorem C2. Okay. So I have another another paragraph, but I think I don't have time to explain it. So I keep it up. And then let me give just some references. So this is a paper of Sekalski, which was our inspiration. This is a paper where I gave the first generalization for isolated critical point. This is a paper that contains another proof, which is given by Euler integration, and then fourth paper is just the preprint with which contains the new results, and it is available on this web server, French web server. So I have finished, and I thank you for your attention.
Okay. Many thanks, Nicolas. ¿Hay alguna pregunta del público? ¿Alguna inquietud? ¿Algún comentario, por favor? A ver, voy a chequear aquí en el chat. Bueno, no, parece que no tenemos. Bien, entonces aprovecharía la oportunidad, Nicolás, para consultarte una pregunta, tal vez que esté relacionada. Es con respecto, dada cualquier F, C2 semianalítica sobre aquel semi-algebraico compacto, si existe alguna cota o estimativa sobre el número de puntos críticos. A ver si los colegas me ayudan en silenciar, por favor, ahí.
¿Puedes repetir? No entendí.
Sí, es con respecto a la cantidad de números críticos que pueda admitir cualquier función C2 definida sobre un X semialgebraico. O sea, sobre la cantidad de números.
Es un problema de tipo Bezout. Y puedes dar una cota en términos de los grados de los polinomios que aparecen en la definición del conjunto. Creo también una cota que depende de los grados y también del número de polinomios que aparecen en la definición, en la fórmula que da el conjunto semi-algebraico. Sí, existen cotas. Existe una generalización del teorema de Bezout, de la cota de Bezout en el caso semi-algebraico.
Ok, perfecto. Ok.
También puedes dar la cota para los números de Betti del conjunto en términos de los grados y del número de polinómicos que aparecen.
Ok. Ok, entiendo. Gracias. ¿Existe alguien que desea tal vez hacer alguna pregunta para el profesor Nicolás? Ok, al parecer no. Nuevamente, profesor Nicolás, agradecerte por la charla que nos has brindado. Y como parte de agradecimiento vamos a presentar certificado virtual que te van a enviar al email.
Ah,
A ver, vamos a esperar ahí que proyecten ahí los colegas. Ok, Nicolás, este es el certificado que se va a hacer respectivo a tu email que van a enviar. Muchas gracias, Nicolás.
muchas gracias, César. Muchas gracias.
Ujú. Gracias nuevamente. Hasta la próxima.
A la próxima.
Ujú. Bien, estimados participantes, doy pase al siguiente presentador. Adelante, Javier, creo.
Gracias, César, gracias. ¿Se me escucha?
Sí, te escuchaban perfectamente,
Ok.
Javier.
Por favor, si pueden cortar ahorita el video para que iniciemos con la siguiente. ¿Se podrá cortar la grabación?